Okay, so today we're going to talk about and problems. So suppose you're choosing cards from a random shuffled deck. What's the probability you choose 5 cards, all diamonds, with replacement? Okay, so if we think about a deck of cards, there are 52 cards in a deck, and there are 13 that are diamonds. So a quarter of the deck are diamonds. Okay, now if we're looking for the probability that you choose 5 cards, all diamonds, with replacement, then that means we're looking for the probability that the first is a diamond, and the probability the second is a diamond, and the probability the third is a diamond, and the probability the fourth is a diamond, and the probability the fifth is a diamond. And in probability, and implies multiplication. So since the cards are being replaced, the probability the first is a diamond is a quarter. The probability the second is also a diamond is still a quarter, times a quarter, times a quarter, times a quarter. So essentially it's 1/4 to the fifth power, which is, if I grab the calculator here, approximately 0.00098. Okay? Now, how does that change if the 5 cards are all diamonds but without replacement? So in other words, after I take a card out, I remove a card permanently from the deck. Now this is still an and problem. So it's still the probability of the first times the probability of the second. But this time it's 1/4 times. It's not a quarter anymore. Why not? Because right here, this is the probability the second card is a diamond, given that the first is a diamond. So now there are only 12 diamonds left out of 51 total cards. And then there are only 11 diamonds left out of 50 total cards. And then there are only 10 out of 49 cards. And then there are only 9 out of 48. So every time that I move through this, I had one less diamond to choose out of one less card. I'm going to determine that total probability is 0.000495. So essentially half, little more than half, of the previous answer, or a little less than half, rather. This is much less likely to occur than this. And if you think about that, that should make sense that it is less likely to occur because there are less diamonds in the deck. Okay? It's important that we understand that both of these problems were and problems. And the probability of an intersection is essentially the probability of A times the probability of B given A. So that notation, the probability that B occurs given that A already occurred. Okay, and that line in between them stands for given. However, the two problems look different because if the events are independent, then A does not affect B, and the probability of B given A is actually just equal to the probability of B. If A does not affect B occurring, then these two probabilities are the same, which is why when I did this last problem, I just did 1/4 times 1/4 times 1/4. But if the events are dependent, then this is a new and unique probability. It is the probability that A occurs or B occurs knowing that A occurred. The probability that B occurs knowing that A occurred. Okay? Knowing whether or not the events are independent or dependent is very, very important. You need to ask yourself, does one affect the other or not? Okay? Now, to clear something very important up. Definition of independence. Independence means that the probability of B given A must equal the probability of B. Now, if I have two events that are mutually exclusive, A and B, mutually exclusive means they do not overlap. So I have A and I have B, and the probability of A and B occurring is 0. Okay? Now, if the probability of A and B occurring is 0, then the probability of A times the probability of B given A must also be 0, which means that one of these two events is 0. Well, if A is 0, if the probability that A occurs is 0, why am I drawing a circle? It's an impossible event. So the probability of A cannot equal 0. So the probability of B given A must equal 0. Now let's ask ourselves a question. If A and B are independent, then the probability of B must equal the probability of B given A. Is that true? Well, the probability of B given A is 0. Does the probability of B equal 0? No, it's a circle. It's a physical thing. B has some probability. B can occur. So this is not a true statement. This is not a true statement. So, period. If two events are mutually exclusive events must be dependent. That is super important. For some reason or other, students get confused and they think independent and mutually exclusive mean the same thing. They actually do not at all. If two events cannot occur together, then one must affect the chances of the other occurring. Period. Last but certainly not least, following represents the marking period grades of students in AP statistics. Are the events being male and receiving an A independent? Okay. Well, what's the probability of being a male? Well, being a male, okay, let's count up the number of males I have. 41, 46, 61, 68 males. Okay, and females are 37, 40, 47. So 68 out of 115. The probability of being a male is 68 out of 115. How about the probability of receiving an A? Okay, that's easy. That's 39. So the probability of receiving an A is 39 out of 115. Okay. Are those events independent? Well, if they were independent, then the probability of A would equal the probability of getting an A given being a male. What's that probability? The probability of getting an A given being a male. Let's find that. Being a male means, well, ignore everything else. 18 out of 68 males. So 18 out of 68 is 0.265. 39 out of 115 is 0.339. So the probability of getting an A is 0.339. The probability of getting an A being a male is 0.265. These two probabilities are not equal. Therefore, being a male affects getting an A. They are not independent events. Not independent events. Okay, that's a good place to stop today.